ethers and thioethers undergo very similar reactions. This is because oxygen and sulfur are chemically very similar. They're in the same column on the periodic table, which means they have the same valence shell electron configuration. If they have that same configuration, that means they are likely to undergo the same bonding patterns in order to get a stable electron configuration in the outer shell. Therefore, it's no surprise that most of the synthesis that we learned for ethers are also applicable to thioethers. And here's an example of one of those. This is a Williamson ether synthesis. In the Williamson ether synthesis, we took an alkoxide ion, reacted it with an alkyl halide under an SN2 mechanism, and the result was an ether. This works exactly the same for thioethers. The only difference here is that instead of an oxygen, there is a sulfur. The sulfur undergoes SN2 reaction, displaces the halide, it takes the bonding electrons with it. The result is the thioether and the halide ion. While they do tend to undergo very, very similar reactions, most or many of the ether reactions also work for thioethers. There are some differences, and generally these differences allow more things to take place in the thioethers rather than limiting what would, rather than being a more limiting type of difference, it's more often expanding on what is already taking place in the ether reactions. And here's an example of that. In the Williamson ether synthesis, we only used primary carbons because using secondary carbons, it allows a greater opportunity for an elimination reaction to take place. In an elimination reaction, what is going to happen is that the alkoxide ion, which is a strong base, will remove a proton instead of acting like a nucleophile and give an alkene instead of an ether. So we couldn't do that. But with sulfur, this does work to give good yields. It's not in the ethers, it did not work. It just didn't work in as well as one would like. You'd get a lot of side reactions. With the sulfur, that's not the case. The sulfur here is a secondary halide right here. Carbon, carbon, carbon. This is a secondary carbon. It will undergo the SN2 reaction mechanism and leave a thioether. And the difference is that oxygen and sulfur aren't exactly the same. Sulfur is a lot larger than oxygen is, which means that its outer electrons are not held onto quite as tightly as oxygen is. If you think of oxygen, it's very, very small. You have the nucleus, you have the s orbitals, and then you have the p orbitals, and that's it. So you have the s orbitals, and then that's it. With sulfur, you have a couple of shells of electrons before you get to the next p orbital that these electrons are in. So those inner orbitals, what they cause is a shielding effect to the outer electrons. They're not held onto quite as tightly. If you look at the ionization energies of elements on the periodic table, as you go down the periodic table, the ionization energy decreases, and that is because of this shielding effect of the inner electrons. So because these are held onto more loosely, the larger elements are more easily polarizable because they're held onto more loosely. And since they're more easily polarizable, those electrons have greater penetrating power when trying to get in tight places. So they're better nucleophiles than smaller ones because they're held onto much more tightly in the smaller ones as the larger ones. So sulfur is a much better nucleophile than oxygen is. So that's one of the big differences. The second is that the alkoxide is a stronger base than this. So the combination of these two things allow this type of reaction to take place in good yields, where in the case of the oxygen it was not happening. And also it allows other reactions to take place that would not ordinarily have even happened in the oxygen, but will happen in the sulfurs, because it's a lot better of a nucleophile than the oxygen is, and a weaker base. Also important to know is that there's a whole different branch of reactions as well, because sulfur is a much larger element. It can get an expanded octet where you get something like this. We'll learn about these type of reactions later on.